Round robin scheduling. So round robin is designed for time shared system. It is very similar to first come first serve. The only difference is that it is preempted by a time quantum. So there is something called a time quantum or a time slice. So this is a small unit of time that we decide to preempt the CPU. So generally it is ranging from 10 milliseconds to 100 milliseconds. So there is a reason why it is limited in this range. We'll see that. Okay. In a round robin scheduling algorithm, the ready queue is treated as a circular queue. The CPU scheduler goes around the ready queue, allocating the CPU to each process for a time interval of up to one time quantum. Okay. We'll see that with an example. So consider there are three processes and the burst time is 10, 3 and 3. And the time quantum is 4 milliseconds. So the CPU will be allocated to the first process, that is P1, for what time? A single time quantum. So it will run from 0 to 4, and when it becomes 4, this is an interrupt is produced and the CPU is preempted and given to the next process. So you can see that the P2 has a burst time 3, which is lesser than the time quantum 4. So what happens is that here there is no requirement of a interrupt. The process itself voluntarily preempts the CPU and hand over the CPU to the next process. Here in this case, P3 also has a burst time that is lesser than the time quantum. So P3 also voluntarily hand overs the CPU to the process who has a remaining time to execute. So in this case, P1. Why? The burst time is 10. So we have already executed 4. So we have 6 remaining milliseconds to be executed. So now P1 will execute for one time quantum. Again, P1 is interrupted. So you may think, seeing the Gantt chart, what is the need of such an interruption? So there may be a chance that during the execution of P1, there is another process that has arrived. So according to RR policy, that process have to be allocated with the time quantum. Okay, but in this case, we don't have no other process. So the CPU is again allocated to the same process. So now we'll see another example. Consider we have process again P1, P2 and P3 and our burst is 10, 5 and 3 and arrival time is 0, 2 and 3. Okay, so initially P1 is allocated with the process for a time quantum of 4. So I've decided the time quantum is 4. So now P1 is allocated for 0 to 4 milliseconds. And then at that point of time, while this is executing, so initially the ready queue has only P1. Okay, while executing, there is another process that P2 has gained. So this is linked to this queue. So this is a ready queue, remember that. And when it is 3 milliseconds, another process came, which is P3. So as I said, this is a circular queue. Okay, so now we are executing P1. Then it is allocated. Then what happens? There is an interrupt that is occurred and the CPU is preempted and given to the next process, that is P2. So now P2 has, say, the next time quantum that is up to 4 to 8. So here as you can see, the burst time was 10, 4 was executed, we have 6 remaining, minus 4, 1 remain. Okay. Then the CPU will be allocated to the next process, that is P3. But P3, the burst time is just 3. So this can voluntarily exit. Okay. So now P3 will run up to 11 milliseconds, that is just 3 milliseconds for its burst time. And once this has completed its execution, when P3 has completed the execution, next P1 will be executing because this is a kind of a circular queue. So now P1 is allocated and since it has 6 to go, you will be allocated with another time quantum. Okay, so remember here P3 has completed its execution. So it will be removed from the queue. So there is now only 2 processes. Okay. So now our P1 will be running for one time quantum, so that is up to 15. Then it is a P2 is allocated. P2 is allocated with 1 millisecond. That is the remaining burst time. So it gets 16 again. So now this has completed. Now again P1 is allocated. P1 is allocated for 2 more milliseconds, that is remaining 16. So that is how the round robin scheduling algorithm works. One problem of RR policy is that the average waiting time is often long. And remember that RR scheduling is always preemptive. There is no version where RR is non-preemptive. Okay. And if there is n process in the ready queue and the time quantum is q, then each process will get 1 by nth of the CPU time in chunks of at most q time units, and each process must wait no longer than n minus 1 into q time units for its next time quantum. So that seems very technical, but it is a very simple concept. So consider we have a CPU time of 100 milliseconds and q is equal to 10 milliseconds. That is the time quantum. And there is n number of process. Then the amount of time that each process will get is 1 by 5th of 100 milliseconds. That is 20 milliseconds. Each process will get 20 milliseconds in a unit of 10 milliseconds. That is, for example, if there is 5 process, P0 will get the first 10 milliseconds, then P1, then P2, P3 and P4, each 10 milliseconds. Then again P1 is allocated with 10 milliseconds. So each process will get 20 milliseconds in a unit of one time quantum, that is 10 milliseconds. Now how much time should a process wait for its next time quantum? That is n minus 1 into q, that is 4 into 10, that is 4 milliseconds. So now P0 has to wait 40 milliseconds to get its next time quantum. That is explained in this particular lines. And the performance of RR algorithm greatly depends upon the size of the time quantum. So the time quantum cannot be very large or very small. Okay. If the time quantum is extremely large, then RR policy is same as first come first serve. And if the time quantum is extremely small, that means the RR policy can result in large number of context switch. Now the context switch can waste a lot of time. Okay, so consider there is a process of 10 milliseconds burst time and consider our time quantum is 12 milliseconds. Then the number of context switches that is required is 0. If it is 6, then it requires 1 context switch. If there is 1 millisecond, then 9 context switch are required. So this can slow the process execution accordingly. And consider if the time quantum uses 10% of its time for context switching. That means that 10% of CPU time is wasted for context switching. So that is the reason why we usually keep the time quantum between 10 milliseconds and 100 milliseconds. So here the context switching time is just 10 microseconds. And the turnaround time can also be improved by selecting the correct time quantum. That is, if the process can be executed in a single time quantum, then the turnaround time can also be greatly improved. This is because there is very few number of context switching. So to say as a rule of thumb, 80% of CPU burst should be shorter than the time quantum. This is the most effective way so that the turnaround time and the average waiting time can reduce and there will be very less number of context switching.